Hello guys, I'm your friend Inside So. I always thought that there's a voice inside of me. They're calling me to do something special, to do something important. And only in this way I can achieve a better life. And yes, this is partly true. Because if you can find your value throughout your life, you won't feel the necessity of living. And that's what I want to say at the beginning of this reading. Here, let's get started with a deep reinforcement learning, playing CartPole the Asynchronous Advantage Actor Critic with tf.keras and eager execution. Why I have to read this? Because it is very simple. I have tried a lot of different ways to apply the reinforcement learning on Mario in the past few weeks, but it just seems don't work according to my own way. So here I was thinking about, why just don't use so I was thinking about, can I just use some policies that created by others? And I found this A3C. It's a reinforcement learning policy that was created by others, and it is proved to be able to work with Mario. So that's why I want to learn this stuff. After this learning, I would be able to create my own agent to play the Mario game, and that should be awesome. That would be awesome. Okay, let's get started. In this tutorial, we will learn how to train a model that is able to win at the simple game CartPole using deep reinforcement learning. We use tf.keras and OpenAI's gem to train our agent using a technique known as Asynchronous Advantage Actor Critic. Reinforcement learning has been receiving an enormous amount of attention, but what is it exactly? Reinforcement learning is an area of machine learning that involves agents that should take certain actions from within an environment to maximize or attain some reward. In this process, we will build a practical experience and develop intuition around the following concepts. The first one is the eager execution. Eager execution is an imperative defined by run interface where operations are executed immediately as they are called from Python. This makes it easier to get started with TensorFlow and can make research and development more intuitive. The second point is model subclassing. Model subclassing allows one to make fully customizable models by subclassing tf.keras.model and defining your own forward path. Model subclassing is particularly useful when eager execution is enabled, since a forward path can be written imperatively. So here comes the concept model subclassing. In general, in my daily routine, I won't use that technology. Instead, I'll use the sequential model or the API functions in Keras. I won't use this technique. But as far as I know, the PyTorch ML library are based on class. If you want to make a model in PyTorch, you're gonna create a class. So this is similar with that. 3. Custom training knobs. We'll follow the basic workflow. Let's say first we have to build our master agent supervisor. 2. We have to build our worker agents. 3. We have to implement the A3C algorithm. 4. We have to train our agents. 5. We have to visualize our performance. Audience. This tutorial is targeted towards anybody interested in reinforcement learning. While we won't go into too much depth into the basics of machine learning, we'll cover topics such as the policy and value networks at a high level. In addition, I suggest reading the paper Asynchronous Methods for Deep Reinforcement Learning by, I don't know how to read that, but it's a person name, which is a great read and provides much more detail into the algorithm. What is CartPole? CartPole is a game. Yeah, literally it's a game. It's a very simple game in which a pole is attached by an unactuated joint to a cart, which moves along a frictionless track. The starting state, the cart position, cart velocity, pole angle, and pole velocity are type is randomly initialized between -0.05 to +0.05. The system is controlled by applying a force of +1 or -1 to the cart moving left or right. The pendulum starts upright, and the goal is to prevent it from falling over. A reward of +1 is provided for every time step that the pole remains upright. The episode ends when the pole is more than 15 degrees from vertical, or the cart moves more than 2.4 units from the center. Here is a general example about how this game looks like. And as you can see, here's a vertical line. It's not a vertical line, it's a ball, I guess. No, it's not a ball. It's a, yeah, you can think it as a vertical line. For this line, it will fall down. Just imagine if you put your pen right on the desk. When you leave it alone, it will fall. And our mission is to let this vertical line keep straight vertically. Establishing a baseline. It's often very useful to establish a baseline in order to properly judge your model's actual performance and the matrices by which you evaluate it. For example, your model may seem to be performing well when you see high scores being returned, but in reality, the high scores may not be reflective of a good algorithm or the result of written actions. In a classification example, we can establish baseline performance by simply analyzing the class distribution and predicting our most common class. But how do we establish a baseline for reinforcement learning? In order to do that, we will create a written agent and will simply perform written actions in our environment. Okay, before we take a look at the code, let us think about this. How can you say you are intelligent? The simplest way is to compare you with a written action people. The written actions does not have logic inside of it, but you do things based on logic. So that's the difference, and that's why you have the intelligence while the written man doesn't. Here we can see he just created a class which named the written agent. This written agent will play the specified game. In here is a CartPole. The argument is environment LAN of the environment to be played on. The maximum number of episodes to run the agent for. The initiate function is the two arguments, the environment LAN and the maxed episodes. The environment equal to gem.make the environment LAN. The maxed episodes equal to the maxed episodes. The global moving average reward equal to 0. The RES cream equal to cream. No, we have to call it Q. Yeah, what is Q in Python or in general ideas? Q is a data structure for representing data. Let's say first in, first out. That's a Q. Then we have defined a function, run. The reward average equal to 0 for episode in the range of maxed episodes. Done equal to false. Save that environment resets. The reward sum equal to 0. Sum of reward equal to 0. The steps equal to 0. While not done. In other words, while this game is still on, we do the following things. We do the environment.step, which means we have to take an action to the environment, and this action is a reading one. As you can see here, he just called environment.action space. From the action base, we take a reading one using a sample function. Then steps plus 1. The reward sum plus the reward. Record statistics. Save that global moving average reward equal to the record episode reward sum 0, global moving average reward, and all those things. I don't know what's that mean because I didn't use it in my project before this reading. The reward average equal to the reward sum plus the reward sum, and in the end we have to divide it by the maxed expose so we can get the final average reward. For the game CartPole, we get an average of 20 across 4,000 episodes. To run the reading agent, run the provided py file. Okay, that's it. That means if we run this game 4,000 times, let's say it will die 4,000 times, and we will get almost 20 average rewards in that game. So for each game we will get 20 reward from that. This is an average reward, I guess. You may ask me why I always recording videos on those stuff, I mean the machine learning. Well, it is very simple because I cannot find any passion from other domains like the traditional programming. It's kind of weird for saying that because I wasn't good at the algorithm side. I mean, if you want to be a good developer or a good programmer, you have to know a lot of useful algorithms. And clearly, I wasn't a smart person, as you know, so I couldn't master those algorithms that much. So basically, I can't do that. So for me, the best way to overcome this is to find a new tool, a new strategy for us to get into complex the problem like the machine learning. Why machine learning is so outstanding? Well, it's simply because for a problem you can do it with the traditional algorithm, or if you can't master that algorithm, you can train a neural network to generate that algorithm. Even this will take you a lot of computing resources, but it is worse for you because you don't have to handle those complex algorithms by yourselves anymore. All you have to do is define a model and feed that model a lot of data, and the neural network will generate that algorithm for you. Okay, now let's get into the core part. What is the Asynchronous Advantage Actor Critic algorithm? Asynchronous Advantage Actor Critic is quite a mouthful. Let's start by breaking down the name and then the mechanics behind the algorithm itself. Asynchronous. The algorithm is an asynchronous algorithm where multiple worker agents are trained in parallel, each with their own copy of the model and environment. This allows our algorithm to not only train faster as more workers are training in parallel, but also to attain a more diverse training experience as each worker's experience is independent. Oh, now I know what the asynchronous was. It's a multi-agent algorithm, I guess. And from this point, I could know that in order to use this algorithm, you must have a strong GPU devices or computing devices, or otherwise it won't work because it got beautiful agents. Advantaging is a metric to judge both how good its actions were, but also how they turned out. This allows the algorithm to focus on where the network's predictions were lacking. Intuitively, this allows us to measure the advantage of taking action over following policy pi at the given time step. Actor critic. The actor critic aspect of the algorithm uses an architecture that shares layers between the policy and the value function. But how does it work? At a high level, the A3C algorithm uses an asynchronous updating scheme that operates on fixed length time steps of experience. It will use these segments to compute estimators of the rewards and the advantage function. Each worker performs the following workflow cycle. 1. Fetch the global network parameters. 2. Interact with the environment by following local policy for number of steps, Tmax steps to terminal state. Calculate value and policy loss. Get gradients from losses. Update the global network with the gradients. Repeat this process. With this training configuration, we expect to see a linear speed up with the number of agents. However, the number of agents your machine can support is bound by the number of CPU cores available. In that case, for my computer got 4 CPU cores, so to the maximum, I could only use 4 agents if I want to, use this algorithm. In addition, A3C can even scale to more than one machine, and some newer research supports scaling it even further. Adding more may prove terminator to speed and performance. Great. Refresher for policy and value functions. If you are already comfortable with policy gradients, then I would recommend skipping this section. Otherwise, if you don't know what policies or values are, or just want a quick refresher, read on. The idea of a policy is to parameterize the action probability distribution given some input states. We do so by creating a network that takes the state of the game and decides what we should do. As such, while the agent is playing the game, whenever it sees a certain state or similar states, it will compute the probability of each available action given an input state, and then sample an action according to this probability distribution. To delve into the mathematics more formally, policy gradients are a special case of the more general score function gradient estimator. The general case is expressed in the form of this. In other words, and in our case, the expectation of a reward function f under some policy network P. Then, using the log derivative trait, we figure out how to update our network's parameters such that the action samples obtain higher rewards and end up with an expression like this. In English, this equation explains how shifting beta in the direction of our gradient will maximize our scores according to the reward function f. Value functions essentially judge how good a certain state is to be. Formally, value functions define the expected sum of rewards when starting in state A and following policy P. This is where the critic part of the LAM becomes relevant. The agent uses the value estimate to update the policy. implementations, let's first define what kind of model we will be using. The master agent will have the global network, and each local worker agent will have a copy of this network in their own process. We will instantiate the model using model subclassing. Model subclassing gives us maximum flexibility to at the cost of higher verbosity. Great. Here we can have a simple glance at the keras model function. I mean, how to use it with the subclass stuff. Here the initial function is it will take two parameters: the state size, the action size. Super actor critic model initiates. Yeah, that means we have to initiate the keras model predefined the initiate function first. Then we give the two parameters, state size and the action size, to the class, so we can use it later in the class function. Self.dense1 equal to layers that dense with 100 with a size of 100. The activation function equal to RELU. So that's the first layer, I guess, or maybe it's not, because we are doing it with the class technology, subclassing technology. Then we define the policy logics layer. It is equal to the layers that dense with action size. So it may somehow output you the action, how many actions you have. For how many actions we have, this layer will output that many of actions. Then we define the dense2 layer. It's also a 100 size of dense layer with the activation function of RELU. And the values, well, the values, let's say it represents for by giving, no matter what kind of states you give it to this model, it will return your value, and that value represents the reward, how many rewards you're gonna get by doing that action, or kind of sense like that. And then another function, call function. For this function, it will take the inputs as a parameter. Then x equal to self.dense1. It takes the inputs as the inputs. It will output x, and for x, we will add another layer. It's a policy logics layer, and for this layer, it will output the logics. It is outputs. So as now as I say, this is just like the functional API in keras. It is the same, especially under the core function. First, you define your layers at the initiate function. Then you do the chain operation. I mean, you take the inputs, you get the outputs. Then the first layer's outputs will be used as the second layer's inputs. Right? It's all the same. And finally, you return the logics, which is the actions. Then you return the values. As you can see from our forward path, our model will take inputs and return policy probability logics and values. Master agent main thread. Let's get to the brain of the operation. The master agent holds a shared optimizer that updates its global network. This agent instantiates the global network that each worker agent will update, as well as the optimizer that we will use to update it. A3C is shown to be quite resilient to a spread of learning rates, but we'll use the ADAM optimizer with a learning rate of this for the game. The master agent is a class. For this class, the game name equal to CartPole. The save directory equal to a directory path. The self that if that path was not existed, we would say we want to make a new directory. Then we create the environment based on the game name. We say the state size equal to the environment that observation space that shape the first value of that. The action size equal to the environment that action space that n. The optimizer equal to tf.string that admin optimizer. The learning rate use login equal to true. We print out the state size and action size. The global model equal to the actor critic model by giving it the state size and the action size. Then we instantiate the model by giving it the proper parameters. So for this class actor critic model, we actually define it at the below. The master agent will run the train function to instantiate and start each of the agents. The master agent handles the according and separation of each agent. Each of these agents will run asynchronously. This is technically not true asynchrony because in Python, because of the GIO globe interpreter lock, a single Python process cannot run threads in parallel. It can, however, run them concurrently, context switch during I/O bound operations. We implement with threads and for the sake of simplicity and clarity of example. So this is the same class. We are in the master agent. We haven't done yet. This is the initial process. We define the global model and we instantialize the global model. Then we have to define functions for that class. So here's the function, train function. If the arguments dot algorithm equal to reading, then we say the reading agent equal to a reading agent with the environment len and the maxed episodes. We run that agent, that reading agent. After that, we return it. But if it's not equal to reading, we'll say the queue equal to a new queue data structure, a pipeline. Workers equal to worker of a lot of things. It all depends on how many CPU cores we have. We use this function to get our CPU cores. Yeah, but here's the problem. I don't know where the worker class or function comes from. We haven't defined it, right? But doesn't matter. Let's say it takes the state size, the action size, the global model, and the optimizer, the queue data structure, and the environment length, the save directory. For each worker, it may have a different dictionary for saving its data. For I worker, for worker in workers, we start each worker. Moving average rewards equal to an empty list. Well, true, we do a loop here. The reward equal to the queue that gets. If reward is not known, we add that reward to the average rewards last. And in the end, I guess we have to calculate the average rewards later. If the reward is known, we break that. Then we join all those. I don't know if it's multi-process or something like that. But we will join those process into this main process by using this line of code. Then we do a graph drawing. We draw out the what? I don't know. Memory class holding or experiments. In addition to keeping track of things either, we'll also implement a memory class. This class will simply give us the functionality to keep track of our actions, rewards, and states that occur per step. Here's a class of memory. First, we define the initiate function, states, actions, the rewards. It's all lasts. Define a store function. It is simple. We just have to add the state, the action, the reward to 3 lasts. Then we define the clear function. It is also very simple. We just have to empty the 3 last states, action, reward. Now we get to the critical part of the algorithm, the worker agent. The worker agent inherits from the threading class, and we override the run method from thread. This will allow us to achieve to achieve the first A in A3C, asynchronous. First, we will begin by initializing a local model and setting up the specific training parameters. So now I understood that for this post they are using the threading techniques to achieve the asynchronous in this algorithm. They're not using multiprocessing but the threading technique. Okay, now let's define the worker class. The worker class is inherited from the threading that thread. We have to set up the global variables across different threads. The global episode equal to 0. The moving average reward equal to 0. The best score equal to 0. The save log equal to the threading.log. We define the parameters that this worker need to receive. It is the same as we call it in here. It is the same. we have to give it that much of parameters. Okay, after we initiate the global superclass, we define our local model by using the actor critical model. Running the algorithm. The next step is to implement the run function. This will actually run our algorithm. We'll run all the threads for a given global maximum number of episodes. This is where the third A, actor, of A3C comes into play. Our agent will act according to our policy function, becoming the actor, while the action is judged by the critic, which is our value function. While this section of the code may seem dense, it really isn't doing much. Within each episode, the code simply does 1. Get our policy, the action probability distribution based on the current frame. 2. Step with action chosen according to policy. 3. If the agent has taken a set number of steps, or the agent has reached a terminal state, then update the global model with gradients computed from the local model. 4. Repeat the whole process. So let's define our run function. It's quite long at the code side, but we will conquer it. We will break it down into pieces and try to understand that. The run function, the total step equal to 1, the MEM equal to memory. Did you still remember the class that we defined, the memory class? It's just a way to manage E3 last. While worker.global episode less than the max episode, we say current state equal to self.environment.reset, memory clear, episode reward equal to 0, episode steps equal to 0, the self episode loss equal to 0, time count equal to 0, done equal to false, while not done will not died. We say logics equal to self.local model. We give it a few parameters. The current state. And then we calculate that logics and we want to know the biggest probability action. The largest probability of an action. What kind of action? What action we should take from this model. Then we take an written action, and we give this action. We take that action to the environment. If done, if it is died, if it's dead, we see the reward equal to -1. The episode reward plus equal to reward. The memories, we're gonna store the current state, the action, and the reward. If time count equal to the update frequency or done, we calculate the gradient. With tf.gradient tape as tape, total loss equal to self.compute loss, done, new state, memory, gamma, self episode loss plus equal to the total loss. We calculate the local gradients. Gradients equal to type.gradients, total loss, self local model that trainable. Push the local gradients to global model. Self.optimizer that apply gradients. Okay, here's the situation. I mean the grades here is the local grades, and here is the global weights, and we just used an function, the optimizer applying gradients to push the local gradients to global model. Then we update the local model with new with new weight. Self.local model that set weights. Self global model that get weights. Why he wanna use the global weights as the local model's weights? I have no idea about that. The memory clean, the time count equal to 0. If done and print information. Worker that global moving average reward equal to that. We must use a lock to save our model and to print to parent data releases. If EP reward greater than worker that best score, with worker that save lock, we save the global model that weights. Yeah, as for the model, here's an interesting fact about the model. The model is nothing but the weights, and the weights is nothing but the matrices. Then we do this over and over again. Let's read the steps one more time. 1. Get our policy or action probability distribution based on the current frame. The action probability distribution. The actual meaning of that is for each action we have it has the probability to be the best action that we should take. So it's a table of action probability. 2. Step with the action chosen according to the policy. Yeah, we take that action in the environment, at the environment. If the agent has taken a set number of steps, or the agent has reached a terminal state. Okay, here's the condition. If the agent has taken a number of steps, I mean how much steps we want the agent to run for one episode, or for only when the agent execute that much of actions we update the data, or the agent has died. If so, we update the global model by using the local agent model's data. When I say data, the data is nothing but matrices, but weights, and all sorts of things. It's just like that. No big mystery behind that. How are the losses computed? The worker agent calculates the losses to obtain gradients with respect to core of its own network parameters. This is where the last A of A3C come into play. The advantage. These are then applied to the global network. The losses are calculated as this, where the R is the discounted rewards. Weight is our value function. It takes the input states. The S here means the states. The pi here is our policy function. It also takes the input states. And A is our advantage function. We use discounted rewards to estimate our Q value since we don't directly determine the Q value with the A3C. Okay, here's the function, compute loss. If done, we say the reward sign equal to 0. Else, we say reward sign equal to the local model result. Get discounted reward. Discounted rewards equal to an empty list. For reward in memory that reward, we reverse the buffer R. What this operation does is to reverse the last, I guess, the rewards matrix or last. The reward sum equal to reward plus gamma times the reward sum. Discounted rewards that append reward sum. Finally, we reverse the discounted rewards that reverse. Why would we call it discounted? It is because we will not use the original reward, but we will use the reward that changed by this expression, gamma times the reward sum. The gamma is a super parameter or parameter for the machine learning project. Yes, we could say here are a series of operations. It all relates to the tf. Yeah, literally, I mean it relates to tf instead of keras. By far, you will not be able to build your network with pure tf.keras with that model, but you have to use some operations with the main tf TensorFlow framework to do that job. So what does the TensorFlow framework does in all those things? Well, the TensorFlow framework is nothing but a computing library. So it's a computing library, and what kind of computing library? Well, it's designed to process tensors, or to be specific, it is designed to process matrices. Yeah, that's all. So that's it. The worker agent will repeat the process of resetting the network parameters to all of those in the global network and repeating the process of interacting with its environment, computing the loss, and then applying the gradients to the global network. Train your algorithm by running the command. Okay, we will not look into the testing section of that. It's not necessary because it is tested by those people carefully, and eventually it turns out, yeah, it works. So so far, let me say this. For this algorithm A3C, how it is different from the traditionally DeepQ network. Well, just one thing, the speed, the training speed, because the A3C algorithms then uses multiple agents. It's like let's say this. For example, if one day you can split yourself into multiple person or into a lot of person. For each of those person, they do nothing but learning, and you keep doing this for one day. If you got 1 million of yourself learning different thing. And after that day, the 1 million yourself combined your back to you, then suddenly you become the smartest person in this world. It's kind of like that, I guess. So the learning speed is a core part about this algorithm. And for other part, I guess it is the same. It is the same way as the deep Q network. Okay, that's it. I will see you in the next video. Bye.